Hello guys, so today we are going to practice International A-Level Paper 3, January 2024. This is for Pearson Edexcel, so let's start right away. Okay, question 1 says, a student had a stack of 500 sheets of paper. He measured the dimensions shown. The student used a balance to determine the mass of the stack of paper. The reading is shown below. State the resolution of the balance. Okay, so there are 500 sheets of paper and the student is trying to measure the mass of this entire stack. The dimensions are shown, X, Z, and Y. Whenever you're going to solve a question, you always have to look at the marks. That is very important to understand how you need to answer this question. So it's just a 1 mark question. And they just asked for the resolution of the balance. The resolution of any measuring device is like the minimum amount of anything that it can measure. So it's over here measuring in kgs and there are 3 decimal points. So like if there was nothing placed in the balance, this is what it would show. And the moment you add something to it, like the least value it could show you would be 0.001 kg. So the resolution of this balance would be 0.001 kg, the least value that it can measure. That is its resolution. Okay, let's move on. So determine the percentage uncertainty in the mass of the stack of paper. Right. So percentage uncertainty has like different formulas depending on what situation you're provided with. So one of its formulas is like, if we discuss the different formulas, percentage uncertainty can be equal to absolute uncertainty, like it is equal to, not can be equal to, over the mean value times 100%, right? Now, this is the easiest formula, and you can use it if you're provided with the absolute uncertainty. But what if you're not provided with it? Like in this case, you don't know what is the absolute uncertainty. So what you can do here is that you can find the absolute uncertainty. So the absolute uncertainty is equal to the range divided by 2. Now, you might be wondering what is range? It's not given here. Uh, Over here, actually, we're not provided the range, but we know the resolution of the balance. And the resolution of a device is actually its range. So this resolution is the range of this balance. Another way they could have phrased this question was like if they provided you like different masses. So they told you like 2.070, 2.171, and 2.181. They provided you like 3 different masses and then asked you to find the percentage uncertainty. In that case, the range would just equal to highest value minus lowest value. So you just subtract 2.070 from 2.181. Okay, but this is different. You don't have like the absolute uncertainty given. You don't have a range of values. So the range is just equal to the resolution of the balance, which is this value. So let's refine the absolute uncertainty. So the range is 0.001 over 2. So that gives you 5 times 10 to the power minus 4 kg. Okay. Now you can substitute it in the formula back. So percentage uncertainty would equal to absolute uncertainty, which is 5 times 10 to the power minus 4 over the mean value. The mean value is your measured value, okay? Because you usually find it by taking several measurements and then calculating the mean. So this is your mean value. So 2.070 and times 100%. So this gives you 0.024 kg. Sorry, percent. 0.024 or 0.024, yeah, 1%. If we keep into account the significant figures over here. Right. So we did that. Now let's move on. I hope that's clear. All right, so part B says the student used Vernier calipers to measure the thickness Y of the stack of paper. Explain one technique he should use to determine an accurate value for Y. So the thing is, if you want to get an accurate value for any measurement, okay, to improve accuracy, what you can always do, no matter what that instrument is or what measurement you're doing, you can repeat the values. Okay, repeat it several times. You can repeat it 3 times or 5 times. The more you repeat it, the better. And then you can take a mean. What will that do? That will reduce random errors in your system. Because if you're taking it several times, so maybe one time by mistake you took a larger reading, maybe another time by mistake you took a smaller reading. So when you take a mean of it and like you repeat it several times and then take a mean, you'll reduce random error. That's one thing that you can say for this answer. See, it's a 2 marks question, so remember you need to mention 2 points, what like for whatever answer it is. And so you could either say that uh, repeat several times, like repeat the measurement several times, and then take the mean. Uh, See, this is like, now this will give you 1 point. If you want to earn the other point, you need to say what error it will reduce. How will it give you an accurate value? So what will it do? This will reduce random error. This is one way of putting it. But then another way you can put it, because it's a vernier calipers. So if it's a vernier calipers, a micrometer screw gauge, something like that, you can always talk about the zero error. So it's either this answer or this on the right. So zero error. Now, if I talk about what is a zero error, let me just show you. So over here, um, this is a Vernier calipers, okay? It's a device you use for measuring very small lengths. Here are its two jaws. J1 and J2 are two jaws of the Vernier calipers. Uh, the bottom scale over here from 0 to 10, this is the Vernier scale. And the top scale is the main scale. So there are two scales. So there are two zeros, right? Now, in an ideal situation, these two zeros, they should coincide when the jaws are closed, like when you're measuring nothing, when there's nothing between the jaws of the vernier calipers, these two zeros, they should perfectly coincide like this. But sometimes that's not the case because it's like a very precise measuring instrument. Sometimes it can be like the zero can be further or it can be a little behind the zero. So that error is called a zero error when these two zeros don't coincide. When one of them is further or behind the other. You call that a zero error. So to improve accuracy in such a case, what you can do is you will first measure the zero error. Measuring the zero error means, like what you do is you see how further the zero is from the other one. You measure that. So you measure the zero error, and then for whatever value you get at the end, you will correct it. Like if you over here, whatever you will measure, uh, because this zero is further, it will give you a different value. So you can correct it at the end. And once you correct it, you'll get the right value. And that value would have a reduced systematic error, not a reduced random error, a reduced systematic error. Why? Because zero error is an error within the system. It's not because of your mistake, it's the system's mistake. So it's a systematic error. So in this case, you can say, check the zero error. Um, and remove it from the final measurement. Again, this is like a 2 marks question, so this just counts as 1 point. You need to tell something else as well, like how would it give you an accurate value? So this will reduce the systematic error. Systematic error, like an error inherent to the system. I hope that's clear.